As we look at this section on partial derivatives, we're going to start with notation because I think that'll be easiest to work with. So if we think about, let's let z equal f of x comma y, then when we use this notation f sub x, this is our derivative. This is the derivative of f of xy with respect to x. Now, with respect to x means we're only taking the derivative of x and we hold y as a constant. Similarly, for f sub y, this is the derivative of f of xy with respect to y. And in that case, your x is held constant. So let's do some examples, and I'm going to go back to the notation and everything else. So let's say example, let's if f of xy equals x to the third plus x squared y to the third minus 2y squared, we're asked to find the derivative with respect to x of 2, 1, and the derivative with respect to y of 2, 1. So let's start with the derivative with respect to x. So we're going to say the derivative with respect to x of f of xy. We don't use the prime notation. That's used for our when we have a single variable, a single independent variable. Here we have two independent variables, so we have to decide which variable we're taking the derivative with respect to. So in this case, the y's are going to stay constant, and the x's are your variables. So the derivative of x to the third is 3x squared, plus the derivative of x squared is 2x, and we keep the y to the third because it's a constant, and the derivative of negative 2y squared is 0. So we could say plus 0, but that's not important, so let's just leave it off. So as you can see here, we brought the y to the third down just like it was a 5 or a 7. It is a constant, so we keep it as such. So let's go ahead and find the derivative with respect to x of the 0.21. So then x is going to be 2, so we're going to have 3 times 2 squared, which is 4, plus 2 times x, which is 2, times y to the third, which is 1. So we have 12 plus 4, which is 16. So this is the slope of the tangent line. So on towards the x direction, we have a positive slope that's very steep. It's a 16. So let's go ahead and talk about the derivative with respect to y. So we're going to say the derivative with respect to y of xy. Now in this case, x's are going to be your constants and y is what you're going to take the derivative of. So the first term we get 0 because the derivative of any constant is 0. And then we have the derivative of, we're going to keep the x squared, and the derivative of y to the third is 3y squared. Minus, now this term is totally y, so the derivative of 2y squared is 4y. So that would be our derivative of this function with respect to y. Now we can also plug in the 0.21 and say the derivative of this at 2, 1 is 3 times 4 times 1 minus 4 times 1, so 12 minus 4, which is 8. So the slope of the tangent line in the y direction is positive, so it's going up. So that kind of gives you an idea of where we're headed with it. But we definitely, the note we need to make here is when you're taking the derivative with respect to one variable, the other variable is constant. Is treated as or considered a constant. Is treated as a constant. All right, so let's look at one more of these. The directions say if f of xy equals the sine of x over 1 plus y, then we're going to calculate the derivative with respect to x and the derivative with respect to y. Now they use different notation. We're going to get into all that. We'll do one more of these once we talk about notation. Now what we have here is we have chain rule because we have the sine of something. So if we take f of xy equal to the sine of something, you can't just take the derivative of that. This is your chain rule happening. So pay attention to the fact that both variables are happening in there. So we're going to say the derivative with respect to x of xy equals, we're going to take the derivative of sine is cosine of the same thing, x over 1 plus y, times the derivative of the inside. Now, when you look at the inside, the derivative of the part, let's make a note over here. Note, we have x over 1 plus y. You could write this as 1 over 1 plus y times x, because the x is completely in the numerator. So the derivative of that is 1 over 1 plus y, and the derivative of x is 1. Now, in order to make sure it does not get absorbed into your cosine, you should move your constant to the front. So 1 over 1 plus y, cosine of x over 1 plus y. So now let's look at the derivative with respect to y of xy. So the derivative of sine of something is, again, cosine of the same thing times the derivative of the inside. Now let's pull that inside out again, and I'm going to let a equal x over 1 plus y. And I'm going to rewrite it to be x times 1 over 1 plus y. I wrote the x out front because it's a constant. So when I take the derivative of this, I made it a so that I would be able to use pretty derivative notation. We're going to keep the, let's rewrite this to be x times 1 plus y to the minus 1. Because you could use product rule, but you're going to have a 0, so I'd rather use chain rule. So I'm going to bring down this x, and the derivative of something to the minus 1 is minus 1 times the same thing to the minus 2, and then the derivative of the inside is just 1. So this gives me negative x over 1 plus y quantity squared. So we can plug this in up here. We have negative x over 1 plus y quantity squared. And I hate for your constants or your terms to get absorbed into your cosine, so let's not do that. So we have this out front, and then we have cosine of x over 1 plus y. So there you can see that the chain rule comes into play even when you're doing partial derivatives. Now that we've seen how to find a partial derivative, let's look at the technicality of it. If f is a function of two variables in this box up at the top, its partial derivatives are the function f sub x and f sub y. We just say fx and fy. And fx of xy is, if you notice this, you have the limit as h approaches 0, f of x plus h comma y minus f of x comma y all over h. So x is kept as the x has the change in x, and the y is kept as a constant. And you can see that happening in the bottom one here as well. So in both of these, we see this to be true. Now down here, I wanted you to see the notations for partial derivatives in the second box. If we let z equal f of xy, this is the notation that we use a lot. It's a nice, pretty easy notation. You also have this notation, and that's a little delta. So we have delta f over delta x, and it looks similar to your dy over dx. You also have the partial of z with respect to x. This one is used just not as much, and we have similar notations in terms of y. So I'd say the three circles are the ones that are used the most. The first two, very much so, and the last two, somewhat. Interpretations of partial derivatives. I kind of alluded to this a little bit earlier. So let's look at this problem. It says f of xy equals 4 minus x squared minus 2y squared. Find your partial derivative at x and your partial derivative of y, and interpret it with those points. Let's start with the fact that this is a paraboloid, and let's talk about the point on the graph. If I have one for x and one for y, then I can easily plug that in and say that the point on the graph is going to be the point 1, 1, 1. So when we talk about the graph, we talk about how the tangent is going to hit that point. All right, so let's look at the derivative with respect to x. The derivative with respect to x, the derivative of 4 is 0. The derivative of negative x squared is negative 2x, and the derivative of negative 2y squared is 0. So then we can say the derivative at 1, 1 is negative 2. Then with our paraboloid, this is a paraboloid here, our tangent curve is sloping downward at the point 1, 1, 1. Now let's talk about y. The partial derivative with respect to y, we're going to take the derivative of 4 to be 0, the derivative of negative x squared to be 0, and the derivative of negative 2y squared to be negative 4y. So when we evaluate it at the point 1, 1, we get negative 4. So again, this tangent curve of the paraboloid is sloping downward at the point 1, 1, 1. Now this one has a steeper slope because we understand slope from where we did algebra before. Let's look at a very practical example here. Earlier we looked at the body mass index, and it's B of m comma h equals m over h squared. M is the mass and h is the height, and we're in terms of kilograms and meters. So consider Joe. He is 64 kilograms and 1.68 meters tall. And the question is to find the partial derivatives and talk about them. So let's use this notation. The partial derivative of b with respect to m. So I like the other notation better, but we should get used to this. By the way, if Joe is 64 kilograms, then he's about 140.8 pounds. And if he's 1.68 meters, that's 6'5.5". Now, those aren't important, but it helps us think about this as a very tall person who is not very heavy. So when we find the partial derivative of our BMI with respect to m, we can think of m as, let me do it over here, so b equals m times 1 over h squared. So the derivative of that with respect to m is 1, so we just have 1 over h squared. So what happens is we're keeping the height consistently and looking at what happens if his weight changes. Let's use the numbers we were given for Joe. So we have 64, 1.68 meters. And when we plug this in, we get 1 over 1.68 squared, which is 0.35. So what this says is think about the labels here. The label for the top was mass, so this is kilograms, and this is heights, which is meters squared. So the 0.035 says that we didn't change the meters, so that's not a big deal. But this says that for every kilogram that his weight goes up, his BMI changes, the Y value is the B, so his BMI changes by 0.035. So that number goes up accordingly. And it's a slope because it's a positive slope, so that indicates it goes up. Now let's talk about the partial derivative with respect to h. So I'm going to move this just a little bit while I talk to you. And let's define b equals m over h squared. B equals m over h squared. So let's call it mh to the minus 2. So when we take the partial derivative with respect to h, we're going to keep the mass. And then the derivative of h to the negative 2 is negative 2h to the negative 3. So we end up with negative 2m over h to the third. Now notice this is going down. So every time his height goes up, since we're keeping mass the same, then his body mass index goes down. It will decrease because we have a negative slope. So let's look at the numbers we were given here. The partial of b with respect to h, 64, 1.68. So we have negative 2 times 64 is negative 128 over 1.68 to the third power. So this gives us about 27, about negative 27. So like I said, if his weight stays the same and his height goes up, then we have a negative slope, so his body mass index goes down. Implicit differentiation works like it did in Calc 1. So the difference is if the variable is being considered as a constant, you consider it as such in your implicit differentiation. So let's talk about the first one. It says find the partial of z with respect to x. So we're going to start off with the derivative of x to the third would be 3x squared, and the partial with respect to x, plus the derivative of y is 0. the derivative of z to the third would be 3z squared, and you have delta z for your partial derivative with respect to z, plus, now here we're going to have the product rule. So I'm going to keep the 6yz, taking the derivative of x to be 1. So here we have the partial with respect to x, plus, now I'm going to take the derivative of z to be 1, and we have 6xy partial z, plus 0 equals 0. Now everything with the z stays on this side, and I'm going to write it out. 3z squared partial with respect to z, plus 6xy partial with respect to z, equals, I'm going to take the x's to the other side, negative 3x squared partial with respect to x, minus 6yz partial with respect to x. Now we're going to factor, and I have 3z squared plus 6xy partial with respect to z, equals negative 3x squared minus 6yz partial with respect to x. Now we're going to divide by the parentheses on the z side, and I'm going to divide both sides by dx, or it's the best way to think of it, divide both sides by dx. So we're going to say the partial with respect to z over the partial with respect to x. So what we're really taking is the partial derivative of z with respect to x. And we have negative 3x squared minus 6yz over 3z squared plus 6xy. So that's our implicit differentiation for our partial of z with respect to x. And now we're going to do it with y, the derivative of z with respect to y. So the derivative of x to the third is 0 because it's a constant. So we have 3y squared partial with respect to y plus 3z squared partial with respect to z, plus product rule again. We're going to take the derivative of y to be 1. So we have 6xz partial with respect to y, plus the derivative of z is 1, 6xy partial with respect to z, plus 0 equals 0. So I'm going to go ahead and factor. Here I have a z, and here I have a partial with respect to z. So I have 3z squared plus 6xy partial with respect to z, equals, on the other side, I have negative 3y squared minus 6xz partial with respect to y. So we can finish it by dividing. So we have the derivative of z with respect to y, and then the top is negative 3y squared minus 6xz, and the bottom is 3z squared plus 6xy. Now, sometimes chain rule is involved, sometimes product rule is involved, sometimes quotient rule. So keep in mind that you just have to think about it carefully. Let's do a very specific example here. Let's let e to the z equal xyz. Now, because you're doing the derivatives, the directions specifically say use implicit differentiation. So when that's the case, you have to show it all out. So we're looking for the derivative of z with respect to x and the derivative of z with respect to y. Using implicit differentiation, the problem says. I'm not going to take the time to write that out. So let's start with the partial with respect to x. So the derivative of e to the z is e to the z with respect to z. And the derivative of, let's take the derivative of x to be 1. So we have yz, the derivative with respect to x, plus the derivative with respect to y. It's a constant, so we don't do that. And the derivative with respect to z, the z is 1, so you have xy, and the partial with respect to z. So I'm gonna skip some steps. E to the z minus xy, and this is all partial with respect to z, equals yz partial with respect to x. So the derivative of z with respect to x is yz in the numerator and e to the z minus xy in the denominator. It's a nice, pretty derivative using implicit differentiation. Could you have done it without implicit differentiation? In this case, yes, but follow the directions and do what you're told. So now we're going to do it with respect to y, the derivative of z with respect to y. So the derivative of z is e to the c with respect to z equals the derivative of y is 1. So we have xz with respect to y plus the derivative of z is 1. So we have xy with respect to z. So I'm going to say e to the z minus, I'm going to bring this over xy, and this is your derivative with respect to z, equals xz, the derivative with respect to y. So we find the derivative of z with respect to y is equal to xz over e to the z minus xy. All right, let's move on. The question is, will they always be that similar? Only because of the way these two problems were designed. If there are polynomials all the way across, then they're going to be very similar. And the way these problems were set up, they are, but not necessarily. So work them out, make sure you do them correctly. In functions of 3 or more variables, we keep more than one variable constant. So you can see how this looks pretty much the same. It doesn't really change what you're doing, but you're only going to pay attention to the variables that are important. So let's look at an example that says, find the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z if f of x, y, and z is equal to e to the xy ln of z. So the partial with respect to x says that x is my variable. Remember that y and z are both constants. So when you take the derivative with respect to x of e to the something, you get e to the something. And the derivative of the something is just y, because y is a constant. So y times x, the derivative is y. And then we keep the ln of z. So we end up with e to the xy times y ln of z. Now let's talk about the partial with respect to y. So it's going to be very similar. The derivative of e to the something is e to the something times the derivative of the something. So the derivative of xy with respect to y is just x. And then we have ln of z. So this answer is e to the xy x ln of z. And then the last one, we're going to do the derivative with respect to z. And e to the xy is a constant here, so we're just going to keep it. And the derivative of natural log of z is 1 over z. So we end up with e to the xy over z. I like partial derivatives. I think they're very fun. I hope that you do as well. Let's look at one more of these. Let's look at higher derivatives. So if f is a function of two variables, then we have f of xy, and their partial derivatives are also functions of two variables. But you can take a second partial derivative. So let's look at some first and second derivatives, the notation. So the first derivative notation, f sub x, means the first derivative with respect to x. Now the second derivative, if we use two x's, that means you just take your second derivative with respect to x again. And if we were to use the delta notation, we would say the second derivative of f with respect to x in both cases. So if we start with x and our next derivative is with respect to y, that means we take our first derivative with respect to x and our second derivative with respect to y. Now it's important to note these go in order, but the partial, the delta notation does not. So here we would start with, we'd say delta y, delta x. So you start on the outside and work your way in notation-wise. I like the f of x notation. So if we start with f of y as our first derivative, we could easily do y for the second derivative, and we have this notation. And then if we start with y, our second derivative could be f of yx, which is the partial derivative with respect to f, and the second partial derivative with respect to x, then we have x, and then we have y. So the second derivative is still going to have to label what it's in terms of. Like I said, I like that f notation better. what we're going to find is that these two often have the same value. Not always, but often. All right, so we're going to find the second partial derivatives of this function. Now, we're going to start with f of x and find that to be the derivative is 3x squared plus the derivative of x is 2x, and we keep the y to the third, and the last one is a constant. And then we're going to find f of y to be 0 plus 3y squared, keep the x squared, minus 4y. So here we have our derivatives with respect to x and our derivatives with respect to y. Now our second derivative, let's take the derivative of x with respect to x, and we get 6x plus the derivative of 2x is 2, and we keep the y to the third. And then you're going to take the derivative of this with respect to y. So we're taking the derivative of x, of the x partial derivative with respect to y. So the first term is 0, and the second term, the derivative of y to the third, is 3y squared. So we get 6xy squared. Now let's switch to the y side. Let's do the second derivative with respect to y. So the derivative of y squared is 2y, so we get 6x squared y minus the derivative of 4y is 4. And we're going to do the same function. We're going to start with the first derivative with respect to y and take the derivative with respect to x. So the derivative of x squared is 2x. Multiplied by that would give me 6xy squared. Now, as you can see, these worked out to be the same, whether you start with x or y. And as I mentioned in the last screen, this happens often, not always, but often. So keep that in mind. It's helpful in some cases. Using this knowledge, we can find partial derivatives of higher order. So like we could find the third derivative, find the first derivative with respect to x and the next two with respect to y. What's interesting is we could find that this derivative is the same thing as when we take the derivative with respect to y first and then x and then y, which is the same thing as this in many cases. If their functions are continuous, then that's when we're going to see this happening. But we can take higher order derivatives, not just second derivatives. So let's look at this problem, and it says calculate f x, x, y, z if f of x, y, z equals sine of 3x plus yz. So we're going to start with the first derivative with respect to x. The derivative of sine of something is cosine of the same thing, 3x plus yz. And then the derivative with respect to x here is just a 3. So our first derivative here with respect to x is 3 cosine of 3x plus yz. Now we're going to take the second derivative, and it's again with respect to x. So we're going to say the next derivative with respect to x. The derivative of cosine is negative sine of the same thing. And the derivative of 3x again is 3. So this means our second derivative with respect to x in both cases is negative 9 sine of 3x plus yz. Now we're moving on to our third derivative. And in our third derivative, we're supposed to find the derivative with respect to y. So the derivative of sine is positive cosine, and we keep the 3x plus yz. And the derivative of y is just z. Oh, that's going to make the next one interesting. So we have this derivative is negative 9z cosine of 3x plus yz. And then if you look back up, we're asked to find the fourth derivative with respect to z. So we're going to say xxyz. Now this involves a product rule because we have a function here and the cosine function here. So I'm going to take the derivative of negative 9z to be negative 9 cosine of all of this stuff. And we're going to say plus, but technically I have minus 9z. And the derivative of cosine of something is negative sine of something. And the derivative of the z here is just y. The derivative of yz with respect to z is y. So our fourth derivative, I'm sorry about that, our fourth derivative is negative 9 cosine of 3x plus yz. And then we have plus 9yz sine of 3x plus yz. It's not overly difficult, it's just sometimes tedious. How is this useful and helpful? So here's a good example. It says the temperature at a point xy on a flat metal plate is given by T of xy equals 50 over 2 plus x squared plus y squared, where T is measured in degrees Celsius and x and y are measured in meters. Find the rate of change of the temperature in degrees Celsius per meter with respect to the distance at the point 3, 2 in the x direction and the y direction. So what we're looking at is we're looking at the rate of change. And if you think about rate of change means slope. So the slope of the tangent line gives us the slope of the surface at that point. So let's start with our derivative of t with respect to x. So when we do this, I'm going to rewrite t before we start. Let's rewrite t to be 50 times 2 plus x squared plus y squared to the minus 1, because it's easier to take a derivative of negative exponent using chain rule than quotient rule. But if you want to do quotient rule, you go for it. So we're going to take the derivative with respect to x, and the derivative of 50 something to the minus 1 power is negative 50 something to the minus 2 power times the derivative of the something. So the derivative with respect to x is 2x. So this gives us negative 100x over 2 plus x squared plus y squared squared. Now we're supposed to find this at the point 3, 2. So when we plug in 3 for x, we get negative 300 on the top. And when we plug in 2 for y, we have 2 plus 9 plus 4 all squared. So I have negative 300 over 9 plus 4 is 13 plus 2 is 15, so that makes 225. So we have this reduces to negative 4 over 3, and we have degrees Celsius per meter. So that's our rate of change in the x direction. So we've got that handled. Now let's look at it in the y direction. So we're going to find the derivative of this function with respect to y. So we're going to say the derivative with respect to y. Again, the derivative of something to the negative 1 power is negative. That's something to the minus 2 power. Times the derivative of y squared is 2y. So we end up with negative 100y over the quantity 2 plus x squared plus y squared squared. So now we're going to plug in the value of 3, 2 to find our rate of change of the temperature with respect to the distance at that point. So we have negative 100 times the y value of 2 makes negative 200 over the bottom is the same. 2 plus 3 squared is 9 plus 2 squared is 4 all squared. So we get negative 200 over 225, and that reduces to negative 8 over 9 degrees Celsius per meter. So this is our rate of change in the y direction, and this is our rate of change in the x direction. A differential equation is when you have the derivative and the variable in the same equation. For example, if you have y prime equals y squared plus 5y, that's a differential equation because you have the variable y along with its derivative in the equation. So we can do partial differential equations, and they're going to include the partial derivatives. And I just wanted you to have an idea that this is where it is. We're not doing anything with it because we saved that for your differential equations course, but you can check this out if you'd like. It's also in your textbook. I really enjoy partial derivatives. I think they're fun, and I hope that you enjoyed this lesson.